Alright guys, so we're back with question number 6, which is a very interesting question. It looks a lot like a pendulum if you look at it, but what it is it's actually a solid cylinder of mass m, which is an internal radius of r, which is rolling without sliding on the inner surface of a bigger cylinder with a radius r, performing small oscillations. So as you can imagine, it looks a bit like a pendulum, but it's not really a pendulum as such because the forces are going to be different, and it's a very interesting question. So let's go on ahead and try and find out its time period.
Let's start with the solution. As I have already told you, any problem of this kind can be solved using two methods. So let's solve this by using energy method. Generally, problems involving rolling are simplified, or the time period can be easily found out by using energy method. So let v be the velocity of this body at this instant theta, and this body is rolling about on this bigger cylinder with radius r, and it is about this center O. Let that angular velocity be omega a. So let's write the potential energy first. Potential energy is, let's say the potential energy is 0 at the equilibrium point. So at this height, this is h. So potential energy is mgh, and h is what we got from the pendulum, that is capital R into 1 minus cos theta. You can use the trigonometry equations, and that is what you get.
So you basically, after a while, after you solve a lot of these problems, you just start understanding what an h directly is going to be.
Yeah.
So you just substitute it, but otherwise, as he said, try out a little bit of trigonometry and you should be able to arrive onto the answer.
And these kind of things help a lot in the exam in saving time.
Yes, definitely.
And then your kinetic energy, be careful while writing kinetic energy when you have rolling bodies. You have half mv square, which is due to translatory motion, which is due to linear velocity, and then you have rotational kinetic energy, which is due to the rolling motion, and this rotation is about this O. As we have already said, it is somewhat like a pendulum, so as you can imagine, it will be going this way from one end to the other. So it is half I naught omega a square plus, these two terms will be involved. So velocity v is capital R minus small r into omega a.
Tell me this, Naveen.
Yeah.
So as the cylinder is rolling, right?
Yeah.
So it'll be rolling around its own axis as well.
Yeah.
So is this going to impart kinetic energy to it, or the half I0 omega a square, I naught omega a square, is that the kinetic energy because of its rotation around O or origin?
Like when you take in any rotational problem, if you calculate the rotational energy about the axis of rotation, all the rotational energies are covered in general.
Okay.
So if you take the main axis of rotation,
okay,
the total kinetic energy is covered. Like these kind of problems will be solved in the rotational chapter, so it should be easy for you people to put this energy term.
Okay, alright.
So V, as you know, is r omega, but here the r is capital R minus small r, since V is from the center of mass.
Okay, you should be very careful about this because this is a very easy mistake to make, where we will directly take r as capital R, but you should remember it's always from the center of mass, and that's r minus small r.
And this is the no slip condition, as you know from the rotation chapter. And then I is m into r minus r square.
So Naveen, hold on for a second. I have a short question. So the moment of inertia that you've calculated, will it be mr square or will it be mr square by 2, where r is obviously capital R minus small r?
Yeah, sorry, it should be half mr square since it is given as solid cylinder. So please make a note of that point. It will be half since it is a solid cylinder. If it is a ring or something of that kind, it will be there won't be any half.
Exactly. So you guys should remember that these are the small mistakes that can ruin an entire question, and these are the kind of things that the IIT JEE exam also relies on, because if you miss it, you're going to miss a factor of 1 by 2 and your answer is going to come out to be completely different. So read the question very, very carefully. Let's move on.
So let's write the total energy term by substituting the above things into the kinetic energy. So total energy is potential energy plus kinetic energy, and the potential is mgr into 1 minus cos theta, plus the kinetic energy after substitution looks something like this: half into m into r minus r square into omega a square plus 1 by 4 m into r minus r square into omega square. So when you differentiate this with respect to time,
so the first term is potential energy,
Yeah.
and the other two terms are the terms of kinetic energy, right?
yeah,
One for translational, the second one for...
this is the potential and this is the kinetic, and the first one is for
Translational.
translational and the second one is for rotational.
rotational.
Now when you differentiate this with respect to time, you get 0 on LHS, and on RHS you have m into gr into sine theta plus m into r minus r whole square into omega a into alpha a. Alpha is d omega a by dt.
So won't we also have d theta by dt there in the first term?
Oh, yes, you have d theta by dt.
Exactly, guys. So as you can see, these are the kind of mistakes that you can make very, very easily when you're in the flow. So be careful and remember to do your differentiation properly, because this is where people make mistakes.
And then you have the third term, half m r minus r whole square into omega a into alpha a, and this is omega a. Since we have taken omega as the angular axle velocity about O.
Okay.
So your final and as I have already said in the first question in the pendulum, sine theta can be approximated to theta if theta is very small.
Yeah. And theta should be in radians.
In radians.
Always remember.
So we use that approximation again. Like in general, you can use these approximations. In the question, it is generally mentioned as theta is very small. So you have to use this approximation, and there are some more approximations also which I'll discuss after this question. So you get the final equation as 3 by 2 m into r minus r into omega a alpha a is equal to minus mg into theta. So you can
Naveen, okay, so this happened really quickly. So Naveen, can you show us how we come to this solution as such? Because we might be missing a step or two.
Yeah, I'll show the differentiation. I'll simplify it.
Yes, let's try that.
Yeah. So it is, these two terms will give 0 is equal to 3 by 2 m into r minus r square into omega a into alpha a.
Okay, so we just added them up.
Plus, yeah, mg r into theta into omega a. That
Okay.
is, this is the first term.
Okay, so omega goes out of the
And then
picture.
omega goes out and then m goes out.
Okay.
Oh,
So-
I'm sorry, I have written this potential energy term. This is r minus r. mg r minus r theta omega a. So 1 r minus r also goes away.
So guys, you realize how very easily, with the kind of flow that we were going with, we can still make these mistakes. So we're showing these all of these mistakes to you because these are the ones that students most commonly make, where we don't complete our differentiation, where we do not substitute r with the accurate value of r, which is r minus r, where we don't completely differentiate and try and directly jump down to the answer. So be very, very careful when you're solving these problems, because it's very easy to make a mistake and lose out on a lot of marks. So let's continue.
So you get alpha A as minus 2g by 3 into r minus r into theta. So from this you get your omega as under root 2g by 3 into r minus r, and your time period is 2 pi by omega.
Okay, so as you can see, it's a fairly simple problem. If we know the steps, if we go one by one, what we are taking away from this problem very clearly is when you have a mixture of physics concepts like rotational motion mixed with simple harmonic motion, you have to be very thorough with both of them, because if you make a mistake in one, you mess up the entire question. B, we need to be very, very careful with our differentiation. C, we need to put in the values and accurately keep tracing those values across steps. When there are multiple terms in an equation, we sometimes tend to make a mistake and tend to forget to put in those words and those symbols as such. So be very careful about these three major errors, and let's move on to the next question. Simple harmonic motion is a very important topic, not because it has a lot of different concepts to be studied. The reason why it's very important is because it can be mixed and matched with a lot of concepts in physics to bring out very interesting problems. We saw the last one on rotation. Now the next one that we have up relates gravitation and simple harmonic motion together, and a very interesting thought experiment. So what we basically have is we have a tunnel that is dug across the earth, passing through its center from one end to the other end. What we now do is we drop a particle into the tunnel. What we need to find out is what will be the motion of the particle, and consequently find out the time period of this motion as such, as in how long will it take to go to the other end, or how will its behavior be. So Naveen, let's try and understand its behavior initially, and then let's try and see how we can go about it.
Yeah. So let's see how are the forces acting on this body when it is at a distance x from the center of the earth. So when it is at a distance x, the mass which is enclosed in the radius x will be producing force on this body of mass m, small m. So that so when you draw the FBD, you have this force F, and then displacement is in this direction, the vector. So F will be equal to minus G m dash small m by x square.
Okay, and m dash will be dependent upon
m dash will be a function of x.
Okay.
So first let's write the mass of earth. Me is equal to 4 by 3 pi capital R cube into density of earth.
Okay.
Let's assume that it has uniform density.
Okay.
So now m dash is 4 by 3 pi x cube into rho e. So from both these you get m dash is equal to x cube by r cube into capital Me.
Alright.
So substitute this in our force. So what you get is F is equal to minus G small m by x square into x cube by r cube into capital M. This goes away and
capital ME, right?
Yeah, ME. Okay. And this leaves a small x. So you get Gm by r cube minus Gm by r cube into x. So from here what you can see is force is directly proportional to x and it is in the opposite direction. So you can say that if you leave a particle in this tunnel, it will undergo SHM. So force is directly proportional to minus x, and your K will be Gm by r cube. So from here you get your omega is equal to under root k by m, which is equal to under root there is this capital ME and small m.
Yes, as we said earlier as well, do not forget to write down all the terms. This is something that happens constantly, and this is not something that you should ever make the mistake of having.
So we get your omega will be gme by r cube. But from the chapter of gravitation, you know G is equal to gm by capital R square. So your time period is 2 pi by omega, and substituting this G into the omega and substituting omega into this, you get your time period as 2 pi under root small capital R by small g.
Okay, so that is the amount of time period that's going to be taken. Students, an interesting exercise for you would be to actually find out the value of the radius of the Earth divided by gravity.
So we'll look at problem 8 now. It says a uniform plate of mass m stays horizontally and symmetrically on two wheels rotating in opposite directions. So here is that plate of mass m, and these two wheels you can see are rotating in opposite directions, and we are given that the separation between the wheels is L, and the friction coefficient between each wheel and the plate is mu. We have to find the time period of oscillations if it is slightly displaced from its length and released. So since there will be SHM because they are rotating in opposite directions.
Yeah, exactly. Okay. So let's see what happens if it is slightly displaced from the mean position.
Right.
So this will be the position of the bar when it is slightly displaced from the mean position. Initially the center of mass was here, but now it is displaced to this point.
Right.
So this wheel will be exerting more normal force because mass is more onto the left side.
Right.
So since the normal force is more, the friction will be more.
Correct.
And here the friction will be less, so there will be a restoring force.
Right. So the restoring force here is friction.
Yeah, exactly.
Which is slightly new in such an arrangement.
Exactly.
Okay. Right.
So it goes on to the other side. When it goes on to the other side, the friction will act again inward because the normal force on the right side roller becomes more.
Correct.
So this is why SHM occurs in this case.
Right.
So let's use these conditions and find out the time period.
Okay.
So first, in the equilibrium case, let's draw the FBD of the plank.
Right.
In perfect equilibrium, there is this R1, R2 and mg.
Okay.
So R1 plus R2 is equal to mg.
Right. Because it's not moving vertically.
Yeah.
Right.
And now when it is slightly displaced, what happens? This is always satisfied if it is slightly displaced also.
Right.
But the torque equations change slightly.
Okay.
So now it would be clear here. This is the initial thing.
Right.
Now it is displaced by x.
Okay.
Now when you write torque about this point,
Yep.
let's say A, this is A and this is B.
Right.
So
we are assuming initial displacement in towards which wheel, A or B?
A.
Okay. So we are taking the torque
about B.
Okay.
So when you find torque about B, you have R1 here.
Right.
So R1 into L, which is the length, that should be nullified by the mg.
Right.
So that will be equal to mg into the distance is half the length plus the extra distance x.
Correct.
So mg into x plus
we already know that
2.
There is no rotational motion. That's why we can equate torque to 0. Right.
So you get R1 as mg by L into x plus L by 2.
Correct.
So from this equation 1, substitute 2 in 1.
Right.
By substituting 2 in 1,
okay,
we get R2 as R2 equal to mg into x minus x by L
right,
plus half.
Note that here R2 is the normal reaction from the wheel B.
Yeah,
Okay.
from wheel B, perfect. Now, so since we know the R1 and R2, now let's find out the friction forces, and the difference between the friction will give the restoring force.
Correct.
So delta F
Okay.
is equal to F2 minus F1,
Right.
which is equal to mu into R2 minus R1.
Right.
That is equal to minus 2 mu mg
Okay.
by L into X.
Okay.
So this is of form F is equal to minus kx.
Exactly. Or minus omega square x.
Yeah, minus m omega square x.
Correct.
So k is equal to 2 mu mg
By L.
by L,
Right.
which is equal to m omega square.
Okay.
So this implies omega is equal to under root 2 mu g by L.
Right.
So from this we get time period as 2 pi by omega.
Right. Brilliant. So you saw in this question that we were given a very interesting system of a plate of mass m being placed on two wheels rotating in opposite directions. So we can nicely see that because they are rotating in opposite directions, a slight disturbance, a slight displacement will actually cause SHM, and we worked that out analytically here. We took the torque about the other wheel, if the plate is displaced towards one of the wheels, we take the torque about the other wheel, and from there. And what is exactly the second equation we take? Oh, the second equation is simply the vertical.
torque, yeah.
Okay. So one of the equation is setting the net
vertical
force equal to
equilibrium,
0.
and the second equation
It's
is
a
torque
rotational
about
equilibrium.
B is 0.
Okay, so we applied vertical equilibrium and rotational equilibrium, and using those equations, we were able to arrive at a relation between the force and the displacement, and from there we proceeded to find the time period and omega. So this was a very interesting problem, and we saw how such systems can actually execute SHM. So this was problem 8.